Hello everyone and welcome to the new course on Numerical Python library, a NumPy library which is written on the top of Python programming language. So what is NumPy library? So NumPy is a numerical Python library which is written on the top of Python. Of course it's an open source project, but why this NumPy got developed and what is the use case of NumPy? So to do all those kinds of mathematical and a logical operation on a multi-dimensional array, you can use the NumPy library. So who created the NumPy? This gentleman in 2005, Jim, started working on this NumPy project. What other things this NumPy can do, like all those kinds of matrix operation, all those linear algebra related functionalities are available in this NumPy. So that is all about what NumPy is. But why we have to use the NumPy? Although we have already available this Python list. So why we need to use the NumPy? So first thing is NumPy is very much fast. And we need some library which is super fast because we are going to use it for the machine learning kind of extremely computational stuff. Now why this NumPy is fast? Because NumPy is not completely written in a Python, but it is written inside the C. And it is very much highly optimized code. That's why the NumPy, all those kinds of operations are very much fast compared to Python list, a core data structure available in Python. There is another useful function of NumPy like a vectorization. So when you are trying to do looping in a Python list, obviously due to this loop, all those slowdown will come, but NumPy use those vectorizations. So at a one shot, there is a parallel implementation of many of those functions. So all those functions execute very much fast. And NumPy is a backbone of majority of data science package like data analysis library. Pandas use NumPy core data structure ND-array. And we have another library, machine learning library, scikit-learn, or I would say sklearn, uses basic structure, the NumPy core data structure ND-array. So that is why the NumPy is very much useful and a very much fundamental library to get started and dive into the data science or a machine learning with Python. Alright, so that is all about what NumPy is and why NumPy. Now let's see what we are going to cover throughout this whole course. So first, foremost and very important part is NumPy installation. So there are two ways we can install it. Either you can just simply install the standalone Python, and on the top of Python with the help of package manager pip, you can install the NumPy library and start working on it. We are going to go with another way like Anaconda installation way. So Anaconda is nothing but a Python distribution, and not just the Python distribution but thousands of different Python packages also got included. And after installation of this Anaconda, by default this NumPy got installed, so you do not need to worry about any kind of installation. Once the Anaconda got installed, automatically this NumPy will be installed. Or by chance if the NumPy is not installed, you can just simply use this pip package manager and install it like pip install NumPy, or you can just simply use conda install NumPy. So that is how we are going to proceed. So in the next video and a subsequent video, we will see how to download and install this Anaconda, and in the upcoming video, we'll see about the Jupyter Notebook, because as a ID throughout this whole course, we are going to use this Jupyter Notebook. Alright, so that is all about the installation part. After that, we'll just straight dive towards the coding part. And let's see what topics we are going to cover in a coding part in this NumPy library. So first thing is, to do any kind of manipulation, we need array. So we will see what are the different ways and what are the different functions are available to create the NumPy array, or I would say the core data type or data structure available in this NumPy library. We will see how to create those ND array. Now interchangeably I will use this n-dimensional array or a ND array or a NumPy array. Eventually I am going to refer it to the same object, so don't get confused. Now once that array got created, we'll see what are the operations and attributes we can perform on the top of those array. Then we'll see what is array indexing and a slicing. So how to extract based on index position some meaningful and important data. Then we'll see one very important concept like a broadcasting, how you can iterate over every single element available in the array, how you can put the binary condition to extract some data based on those conditions. Some mathematical functions like a trigonometric function, exponential function, ceiling, floor, and many more mathematical functions we'll see, and how we can apply all those functions directly on this ND array. Arithmetic operation, so how you can do all those element by element operation on the top of ND array. One very important concept like a copy and view, how you can sort the element inside the array or how you can search the specific element in array. Some of the statistical functions like a percentile, quartile, mean, median, and all those things we'll see. At the end, we'll see some very important functions available in this linear algebra module, lineage module I would say, in a NumPy library. So these are the topics we are going to cover throughout this whole course, and I am very much excited. So see you into next video. We'll get started with a downloading of Anaconda installation, and afterwards we'll get started with the Jupyter notebook. So to download the Anaconda, let's go to the anaconda.com/download. Now this Anaconda is available for all three major operating systems like Windows, Mac and Linux. The installation process of Windows and a Mac is quite similar. So it is having a graphical installation. You can just straight away double click on it and just as usual installation process you can follow. For the Linux, there is a one shell script sh file is available, executable. So you can just execute from your terminal and just follow the instruction. Okay, now I am on a Windows machine, so I am going to continue download it for the Windows machine, and it is available for two different versions like Python 3.7 and 2.7. Again, it is available for the 64-bit graphical installer or a command line installer. So I am going to continue with the Python 3x family of versions. So it's a 3.7 version and graphical installer. So 64-bit graphical installer. I'm not going to download it because I have already downloaded at my local machine. You can just click on it and you can download it. So let me just go to the place where I have downloaded. Okay, so you can see I have a Anaconda is available, which is close to around 647 MB. Let me just double click on it and it will start the installation. Okay, press next. So it's a usual Windows software installation process. I agree. You want to install just for you only. And what is the place you want to install? So let me just browse on it. Let me create one place, let's say on a C drive. Already one Anaconda version is already installed on my machine, so I'm going to create one more folder, let's say Conda, and let me press OK. Let's just press next. Now it is saying that you want to register this Anaconda as your default Python 3.7. Yes. And there is a one more option like add Anaconda to my path variable. So once you select it, it will become a red, and it is saying that it's not recommended, but I would highly suggest you to select this particular option so that your path variable get appended by the Anaconda's Python. So when you start the Python from the command line or from the terminal, automatically this Python path will be taken into consideration. Okay, after that just press install and it will start installation of Anaconda on your local machine. So it will take little time to get it installed. So I'm just fast forwarding my video till the installation got complete. Alright, so installation is almost completed. Let me just press next. And it is asking me to install the Microsoft VS Code, but it is not mandatory, so I'm just skipping it. And let me just unselect this both option and let's just press finish. Alright, so Anaconda installation has been completed. Virtual environment. Alright everyone. So in the last video we have successfully installed this Anaconda on our local machine. The next is we need to install the NumPy library and get started with the Jupyter notebook. As I am on my Windows machine, so let me just open the command line prompt. If you are on a Linux or a Mac machine, you can just simply open the terminal. So to open the command line prompt on a Windows machine, you can just simply open from the start menu and just type cmd and just type conda . So it has given us a lot of suggestion that how you should use this command. That means the Anaconda successfully got installed on our local machine. Next is we can just simply type Python and it will open the Python command line prompt. Let me import NumPy library and you can see it got successfully loaded on our local machine. That means NumPy is already installed. If it is not installed, you can just come out from here and just type pip install NumPy. So it will download this NumPy latest package from the central repository and install in your local machine. Now it says that requirement is already satisfied. In my case, that means this NumPy is successfully installed on my machine. So either you can install through this pip installation way or a conda install NumPy way. Now next is we need to start the Jupyter notebook. So let me just type Jupyter notebook. Now this Jupyter notebook also pre-bundled with this Anaconda. So you do not need to install anything about the Jupyter notebook. Alright, so Jupyter notebook successfully got open on my local host 8888 port. From here I can create a new Jupyter notebook and let me create a brand new Jupyter notebook based on Python 3 kernel. I have already hide it, so let me just show it. So toggle header and toggle toolbar. Let me just rename the notebook name. So NumPy test. Here I can write all those Python code. So let me import NumPy as NP. Now as NP indicates that there is a alias name we are going to refer to this every single function available in this NumPy library. To execute this one, you can just simply select or press this run button or shift enter or a control enter. Now this particular cell got executed and it has not returned any kind of error. That means the NumPy library also successfully got loaded in our Jupyter notebook Python 3 kernel environment also. Alright, all our environment got successfully set up. The next is we need to start diving into the different functionality available in this NumPy library. So see you into next video. We'll get started with how to create a very basic task in a NumPy, how to create a ND array. Alright everyone. So we have successfully set up this NumPy library on our local machine. Now time to get our hands dirty with this NumPy coding part. So first foremost thing we need for any kind of array or a data manipulation, we need an array. So in this video and a subsequent one or couple of more video, we will see how we can create a NumPy array or ND array, a core data structure available in this NumPy library, and what are the different functions are available to create this array. So let me just switch over to Jupyter notebook and I will show you how we can create this ND array. Alright, so I have already created one brand new Jupyter notebook and renamed it to NumPy. Let me just hide all those toolbar and header so we'll get more space. First of all, let me just load this NumPy library, import NumPy as NP, and to execute this particular cell you can just simply use shift enter or a control enter. Let me just make heading like NumPy array creation, and I'll just make second level heading, and along with that, this is the first video of array creation part. Alright, so this is just the markdown cell I have created. Now first is we are going to create a one-dimensional array, then we'll proceed towards the higher dimension like 2D or a 3D array. So one-dimensional array will create from the core data structure available in a Python list. So let me just create one list, and from this list we are going to create this 1D NumPy array. So my list, let me give any number like let's say 2, 3 and 4. Now in this NumPy library I can refer to every single function with this NP. I do not need to write whole NumPy. That's why we have given here the alias name. Now to get the suggestion inside this Jupyter notebook, after pressing np dot, you can just simply press tab, or you can just type few characters and press the tab. It will give you suggestion based on what character you have already typed. So we have one functions are available in this NumPy library array. Now in this array you can just simply pass the my list what we have created, and let me just execute it. So you can see it has written a NumPy array or ND array having a value 2, 3 and 4. Still we haven't assigned this to any variable, so let me just assign it to the my_array. Alright, so now we have created our first one-dimensional NumPy array. We can even verify with this type function available in a Python that what is the type of this NumPy array. So that is a numpy.ndArray kind of object. So from this list you can create such a kind of one-dimensional NumPy array. Next is let's create a 2D array. So let me give here the name like myArray_1D. So it will be much better for us to understand. The next is we are going to create a 2D array. Now to create this 2D array, you can pass the list of values or in a brackets inside the bracket, or I would say list inside the list or a list within a list. So we are going to use the same function like np.array, and inside that I can just simply use brackets and bracket within a bracket. So first bracket indicates the one dimension. The second bracket indicates you are going to create the array of 2 dimensions. Let me give any number like 2, 5 and 6. So you can see this one, this highlighted green part, that is just one single list, and those lists we have kept inside the list. Let me put comma, and after that one more list we are going to add. Let's say 4, 0. Let me give any number like -3, and let me just assign it to myArray 2D, the value of 2D or myArray_2D. Now you can see compared to the first one, we have 6 values are available, and this is list within a list. Now all those values we have supplied till now, that is a integer value only. But suppose you want to create array where the values are float. So let me just copy it, and I'll just make one number as a float or 3.0. So it will return every single value or element as a float value. You can even give explicit argument also that every single element I need like integer only, or I need float only, or any kind of complex object also. Let's say same array we'll create, but one more argument we'll supply like D type. So it will be a, let's say, float. So you can see exactly the same thing it has written. Along with the float, you can give other argument like complex also. So it will return every single element as a complex number. There is a one more data type also you can use, like a np.bool. So it will convert every single value into Boolean value. So you can see everywhere it has returned true wherever the number is not 0, and wherever the number is 0 it has returned a false. So till now we have just supplied all those integer or a float. Let's say you want to put non-homogeneous element like a string also. So you can just simply use, let's create a simple one dimension. So first argument like a hello, I want to put, let's say, Boolean value also, then I want to put the integer also, then I want to put, let's say, float also. And let me just execute it, and you will see the difference that every single element or a value in this NAND array, it has converted into string. So this character indicates that it is kind of Unicode value. So one thing is clear, that NumPy array cannot accommodate non-homogeneous type of element, but even if you supplied non-homogeneous kind of element, it will be mapped to lower level precision value. So you can see the true here Boolean value becomes the true as a string, 23 as an integer become 23 string, and 5.6 also become string, because you just cannot convert this hello into integer. After all, everything is just a set of character, or it's kind of set of string only. So this is a 1D array and this is the 2D array we have created. Let's say we want to create a 3D array. So ND array. Now here, instead of 2 brackets, we need to supply the 3 brackets. So 1, 2 and 3. Let me give 2, 3 and one more argument like 1, 4. Let me just execute it. So this looks like a 2D array, but it is actually a 3D array. Let me put some more data so you will get idea. I'm just going to copy the same element. Afterwards we will change it. Let's say 4 to 5, I will make it here 2. This is just for the understanding purpose. Now once we learn about what are the different attributes you can apply on the top of this ND array, you will be able to understand that what are the size, what are the dimension associated with individual array. So those attributes and some methods which we can apply on the top of array, we will see in a next video. So meanwhile, let me just assign it to my array 3D. Alright, so we have a 1D array, we have a 2D array, and we have a 3D array. So in the next video, we'll see what are the attributes we can apply on the top of these arrays. So see you into next video. Alright everyone. So in the last video, we have successfully created a 1D array, 2D array and a 3D array. Now let's see what are the attributes which we can apply on the top of those NumPy array. So we have already my array 1D. Let's say I want to see the size of this or a shape of this 1D array. So it will be a 3, 0 because we have a 3 element. Before that, let me just put, or let me just display all those array. So we'll get idea. Alright, so this is the first element or a 1D array. This is the 2, it doesn't look good actually. So let me just put a print statement. Alright. Let's put some more prints so it will be separated. Alright, so this is the first, second and a third. Same way, let's print the 2D array shape. So it will be a 2, 3. That means we have a 2 rows and a 3 column. Eventually, the 2 values in a 1 dimension or a first axis and a 3 values in a second axis. Same way, for 3D also we can get the shape like 1, 6 and 2. because this whole is a 1, then we have total 6 rows and a 2 column. So along the first axis there is only 1 value, along the second axis we have a 6 values, and along the third axis we have a 2 values. Let's say we want to grab the length of this array. We can just simply use the len inbuilt functions available in this Python. So my array 1D, so it will be a 3. Let's go with the second one, 2D array, so it will be a 2, because we have a total 2 elements. So this is the first element, this is the second element. Same way we have a my array 3D, so it's just the 1 because we have just the 1 element. Now if you observe here, the len function has returned what are the values are available in this first axis, 3, 2 and a 1. We can even grab the size of individual arrays. So my array 1D, let's say size, so it will be a 3 because we have a total 3 elements are there in this 1D array. Let's say my array 2D dot size, so we have a total 6 element in this 2D array. And how many elements we have in a 3D array? So it will be a 12. So 3, 6 and 12. We can even get the data type also. So all data types are as of now integer only. So let me just put D type, and you can see all those integer 32. But we have earlier created this float kind of array also. So let me just select this one, and we will apply this D type. We can just simply apply D type here also, so it is a float. This is just to show you that how this D type will return different data types supported by this NumPy library. Same way you can go for my array 2D D type also, so it will be also integer 32-bit only. We can even grab the n dimension. So how many dimensional those array is? So first array we already know, 1D array and dim, so it will be a 1 dimension. Same way for the second, it will be a 2 dimension, and my array 3D will be a and dim will be a 3-dimensional array we have created. We earlier created this complex also, so we can even put it here. Let me put it into another line. So D type is equal to np dot complex, and you can see it has returned the complex 128 bit. Alright, so these are the attributes you can apply on the top of arrays. So till now we have just simply created a 1D array, 2D array and 3D array, and we have seen what are the attributes we can apply on the top of it. Now for you, you can do the exercise and you can keep creating the different array like 1D and 2D, so you will get to know about it, how this brackets and brackets inside the bracket will work, and it will behave like a 1D or a 2D array. Mostly for the images kind of data will be dealing with a 2D array or a 3D array. When you are dealing with the any kind of time series data, mostly it is a kind of 1D array. So based on the different types of data, you have to deal with this 1D array or a 2D array or a 3D array. But most of the tasks in a machine learning, you can max go to the 4D array, or max it will be a 5D array, not more than that. And the main objective behind this library is to use very high performance computational this core data structure ND array inside this computational part of this machine learning. Alright, so these are the very simple one function we have seen how to create the array np.array. There are some more specialized functions are available to create this ND array. So those function we'll see in a next video. Alright everyone. So in the last two video we have seen how to create a NumPy array and what are the attributes which we can apply on the top of NumPy array. Now in this video we'll be learning about some of the special function to create those NumPy array. The first function we are going to learn is a range. So it will be a range. Now this particular function requires a 3 argument. All those arguments are not mandatory. So first argument will be something like a start, end, and last one is a step size. Let me just comment this one, and we are just going to proceed range function. Let me give just the 10 only. So by default the value of start will be 0, the default value of step will be a 1, and end value you have to provide it. Let me just execute it. So you can see, based on the default value 0 as a start value and 1 as an increment value of step, it has generated the array where the values are ranging from 0 to 9. Upper limit is always excluded. Let's say instead of starting from 0, you want to create an array where the values are starting from, let's say, 5. So I can just simply use first argument as a 5, which is nothing but the start, and the second argument as a 10. So you can see now it has generated the sequences which is starting from 5. But every time in both the case the sequences are incremented in a step size of 1 only. Let's say from 5 to, let's say, 20, instead of starting with 1, let me just execute it. So now in this case it is starting, it is step size is 1. Instead of 1 step size, I want to keep the step size, let's say, 2. Now you can see it is incrementing in a step of 2. You can even go at a negative side also. So let's say from -10 to 5 in a step size of 3 I want to generate it. So from -10 to -7 to -4 to -1 to 2. Alright, so this way with the help of range function you can generate the sequence. There is another counter alternative option to generate the sequence are line space. Now this line space require again the 3 argument, start, end, and the last argument won't be a step, but between start and end in how many total number of division you want to make. Let's say from 0 to 10, it has divided this whole array into 50 different values. Let's see the documentation of this line space. So you can see the first value is start, then stop, and number is by default 50. So you want to divide this 0 and 10 into 50 division, and every single interval is equal in size. Let's say instead of 10 I want to divide it into 3 chunks only. So 0 to 5 to 10. So there is a 3 value it will generate it. And all these 3 values are equally spaced. Let me go from, let's say, -10 to 10, and I want to divide it into, let's say, 10. So from -10 to 10 it has divided whole range into 10 different numbers. This is a range we have learned, and we have learned about the line space. One more is a log space. So it will be a log space. Same way here also we can give like 1 to, let's say, 10, 10. And you can see it has written like a 10 raised to 1, 10 raised to 2, 10 raised to 3, 10 raised to 4. Now instead of 10 log, I want to go for 2 log, or 2 values only I want to generate it. So it will be 10 raised to 1 and 10 raised to 10 only. Now one more argument, we can supply it like a base. Now by default base is 10, we can even go for base is equal to 2 also. So let me give first as a 1 to 10. How many number I want to generate? Let's say 5 only, and base will be, let's say, 2. So 2, 9.51. Let's say I'll just keep it 10. So it will be a 2, 2 raised to 2, 2 raised to 3, 2 raised to 4, 2 raised to 5 till the 2 raised to 10. So because this is the 10 we have given it. So this way you can generate the sequences with these 3 functions available in this NumPy, and all these 3 functions return a NumPy array. Let's see some more specialized function like let's say you want to generate a NP array where initialize all those values with a 0. So you can use the function like a zeros. Here you can pass the dimension, let's say 3. So it will generate a vector, or I would say a one-dimensional array having a 3 values and all those values are 0. Let's say instead of 1 dimension you want to generate for the 2-dimension matrix. So you can go with the argument like in a form of tuples you need to provide. Let's say 3, 5. So 3 rows and a 5 column matrix it has generated where all the values are 1 or 0, sorry. Same way we have another function like ones. So all values will be 1, and just like what we did for the zeros, we can even create a 2-dimensional matrix where every single values will be 1. Let's create a 3-dimensional matrix. So first axis is 3, then second axis is 4, and third axis will be 5. So you can see this is 1, this is another one, and this is another one. So there is a 3 values in a first dimension. Then we have 4 values. So every single matrix has a 4 row and a 5 column. We have another function like a full. So let's say you want to fill up every single value or element inside the array with some specified value. Let's give the shape first. Let's say 2 rows and a 3 column matrix I want to generate, and every single value I want to fill up with a 5. So you can see 2 rows and a 5 column or 3 column matrix it has generated, and where every single value will be 5. Let's say we want to generate the diagonal element. You can just simply use the I function, and here you can pass the dimension, let's say 5. So 5 cross 5 matrix it will generate where only diagonal values will be 1, remaining all values will be 0. You can even generate the empty matrix where there is no initialization will happen. So let me give 3 cross 4. So 3 cross 4, that will be a little high, let's say 3, 2. So now it has generated 0. So every time you do some different number it will generate. So don't think that it is any kind of random number, but it is uninitialized, and whatever value exists on your hardware it will just fetch up, and mostly you will get the values near to 0. So if you observe here, it is e raised to minus 307. That indicates that it's a very low numbers. Alright, so in this video we have seen many functions and many of the specialized functions to create a NumPy array. Now in the next video we'll see a random module. So through random module how you can generate a NumPy array. Alright everyone. So let's learn about the random module available in this NumPy array and how you can generate the random number matrix, or I would say array, in this NumPy library. So let's use the np.random. Now every single functionality of this NumPy library available in this random module, and inside this random module all those functions of random data generation has been written. Let's use the very first function like a randint. Let's say I want to generate a random integer between 0 and 50. So if I just execute it, any random number between 0 and 50 will be generated. Let's say if I again do it, it will be a 42. If I again try it, 5. So now if you just keep executing this, you will feel like it's a random number. But frankly speaking, this is not a truly random number, but this is kind of pseudo random number. Suppose if I give you this particular function and I want you to execute on your Jupyter notebook on your machine, do you think that the same number will be returned after executing this one? So suppose if I want to reproduce the same result every single time, there is a one more function is been given like np.random.sid. So what sid will do, you can just supply any integer like let's say 0, and if I just execute it, let me execute it again. So first time it has generated 44, again it has generated 44. So that means that this 0 has been now aligned to this 44, that every time you try to execute this random integer 0 to 50, it will always generate a 44 only. But suppose the same command, if you just execute it once again in another cell, the new number will be generated, because you are trying to execute this random integer generation function the second time after you have executed or set the seed value. Now this seed value, once you change it, let me give 12, and immediately the number will change. But once you execute, or again if you execute it, every time you will return the 11. So the important thing about the seed is that this random number generation are not truly random, but they are again dependent on the seed. Alright, now instead of just one single number, let's generate let's say 10 number. So you can see it has generated 27, 6, 49, 2, 0. Just remember, if I execute it again, every time it will generate the same number. But the same thing, if I do it in another cell, it will generate completely different sets of number. So whenever you want to reproduce the same result, you can always set the seed to the same number, and if you try to execute on your Jupyter notebook or in your machine, you can just set the seed same number and you can reproduce the same result. So this random integer function eventually will generate the random number between this lower values and higher values, and the third argument will have given like how many total random number you want to generate. Let's see one more function. It will generate the uniformly distributed data. So np.random.rand. Let me give just 3. So you can see 3 values it has generated. It is a uniformly distributed data. Now instead of just the one dimensional, we can even go with the 2-dimensional matrix also. So it has generated this 2-dimensional. We can even go for the 3-dimension also. So let's say 3, 2, 5. Oops. So total 3 matrix it has generated. Every single matrix is 2 rows and a 5-column matrix. Alright, so these are the uniformly distributed data. But how we'll verify these are the uniformly distributed data? So we'll see. Before that, let me generate the normally distributed data. So I'm just going to copy it and put it here. Now instead of rand function, I'm just going to use a rand end. So it will be a random normally distributed data. Let me comment this one. So you can see this is normally distributed data, but still you won't have any idea whether it is truly normally distributed data or not. So we will display this data with the help of this matplotlib library, and I will convince you that these are the truly uniformly distributed data. Alright. So to display this data, we are going to use this matplotlib library. So matplotlib.pyplot as plt. Alright, and we are just going to use this hist function, and here I am just going to pass it this first argument. So it will generate the 3 values only. Let me generate few more. Let's say 10 uniformly distributed value and display it as a chart. Let me just put semicolon here so it won't display again. So we have just a 10 value, so it doesn't look like a truly uniformly distributed data. Let's just increase 100 value, so it looks like little bit uniformly distributed, but as we go higher and higher number and more data will generate, it looks like a uniformly distributed data. Let me go even high. Alright, you can even increase the bin also. So as of now the bin size is very less. So let's say bins, I want to keep it like a 50. Alright. So this is the uniformly distributed data. Let's use the same way in another cell. Now first I'll just going to generate the 10 values only, but normally distributed data. Alright. Let me comment this bin part as of now. Alright. See, this doesn't look like anywhere a normally distributed data because we have generated a very less number of data. Let's go for a 100 one. So now slowly this bell shape kind of curves are emerging. Let's increase 1000. Alright, so it looks good. Let me increase now the bin size. Alright, so it is looks like a normally distributed data. Let me increase by 10,000. Now it looks very much nice. Alright, so this way we can generate the random data, uniformly distributed or normally distributed data. Now to generate this uniform distributed data in some other range. Now if you observe here, all those data are ranging between 0 and 1 or somewhere around the 0 only. But you want to change the mean or you want to change the height of uniformly distributed data. So we can use like np.random.uniform. So between 3, let's say, and 5, I want to generate the 10 values. Alright, and the same thing I am just going to put it inside the hist. Alright, let me keep the 100 values. So now slowly it is moving towards the uniformly distributed data, but this thing we have generated earlier also, but in that case we have a data range from 0 to 1, but now we have a data range from 3 to 5. Let me increase it to, let's say, 10,000 or 1 lakh. Yeah, so it looks very fine. Alright, same way we can even generate the normally distributed data, but now in normally distributed data, the range or normally distributed data has been defined by the two parameters, which is mean value and a standard deviation. So I am just going to use random.normal, and the mean value, let's just keep 3, and normally or standard deviation will be 5, and we are going to generate the 1 lakhs value. Let me increase little bit bins. So bins, let me just keep 20. Alright, so here the mean value will be little bit, let me decrease this mean value so it will be okay for us. Alright, so now you can easily see that mean value will be somewhere around 3, and the variation, or I would say the standard deviation around the mean, will be very less, somewhere around 1 only. We can even have a overlapping of these two plots on a same graph also possible. So let me just keep it here. Alright, so one graph or uniformly distributed data is little bit hidden. Alright, so we have seen how to generate uniformly distributed data, randomly distributed data, and we have plotted also. Now one more last function we are going to see is a shuffling. Let's say I'm just going to use this function arange, what we have seen in the last video, and I'm just going to add it or assign it to the array. Now I have a values like 0 to 9. Let me keep it here so it will be nice. Alright, now I'm just going to use this random shuffle, and let me just supply array. So it will just shuffle all those values available in this array. And let me again display this array because it will do in place modification. Let me do it again. Alright, so that's all about this random number module. You can practice yourself and generate more random data and convince yourself with this such a kind of graph that whatever data has been generated, that is aligned to your mathematical theory. Alright, so that's all about this video. See you into next video. We'll see some more functionality of this NumPy library. Alright everyone. So in the last few videos, we have seen how you can create a NumPy array. Now time to learn about the indexing and slicing. So what does the indexing mean? So let me just create one NumPy array. A one-dimensional array indexing we will see in this video, and a 2D array indexing we will see in a next video. So we are going to just simply use np.arange. Let me generate the numbers between, let's say, 5 to 20, and let me just print it a. So you can see we have a total 15 number it has generated from 5 to 19. Now here the indexing means, suppose you want to extract some particular number, let's say 10. or you want to extract the range of numbers, let's say 15, 16 and 17, or some numbers like 6 and 18 only you want to extract it. So every single value has been associated with some positive number, and that is called as a indexing. In NumPy, the indexing are starting from 0. So 0 is pointing to 5, 1 is pointing to 6, 2 is pointing to 7, and so on. So let's say we will try to grab 10. So this is 0, 1, 2, 3, 4 and 5. So 5 number is pointing to the number 10 in our array what we have just now generated. So let's say if we want to grab the 10, we can just simply write a bigger brackets, and inside the bigger brackets we can give the indexing number. Let's give the 5 and let's just execute it. So you can see it has returned the 10. Let's say I want to grab the 5 itself. I can just simply use 0 because 0 is pointing to 5. So it has returned the 5. So this way individual numbers indexing works in this NumPy array. Let's say we have a total 15 array. So I'll just do 15. So it has immediately given me the error because 15 is pointing to nowhere, because these are just the 15 element and here the indexing are starting from 0. So the last value will be 14 only. So if I try to do 14, we have got the last number 19. Alright. So this way you can get the individual number or individual element from the NumPy array. Let me display it again. Now suppose you want to grab the range of numbers. Let's say from 8 to 12, I want to grab it. So 8 has been pointed by the indexing 0, 1, 2 and 3. So 8 has been pointed by 3 and 12. So 0, 1, 2, 3, 4, 5, 6, 7. So 12 has been pointed by number 7. Alright. Now suppose if I want to grab from 8 to 12, I can use the same bigger brackets. But now instead of giving just one number, we have to give the two number, like lower range and a upper range. So first we'll write like a lower range. So let's give 3. And after that, to separate this lower range with the upper range, you just need to put the colon. Now upper limit is always excluded in case of this NumPy array. Same way what we used to do in a string and all other Python mechanism. So I'm just going to put it here instead of 7, 8, and let's just execute it. So now you can see as I kept it 8 is pointing to 13. So 13 is excluded and it has returned me 8, 9, 10, 11 and 12. So you can always practice yourself. Let's try with one more. Let's say from 6 and 7 I want to grab it. I can just simply use 6 has been pointed by number 1. I want to go till 7. 7 has been pointed by number 2. So I have to keep it here through 3. One more. So it has written 6 and 7. Here the negative index also works. Like it works for the string class in a Python also. So the last value is pointed by number -1, then -2 and -3. So let's say if I do a -1, it will return me the last number. If I want to get the second last, a -2, that will be a 18. Suppose with negative indexing you want to grab, let's say 12 to 16. So I can just simply use a. So 12 has been pointed by in negative number. So -1, -2, -3, -4, -5, -6, -7 and -8. So I can just simply put -8 colon. Now I have to go till -16. So -16 is nothing but -4. But I have to increase by 1. So I will just keep it -3. So you can see now I got 12, 13, 14, 15 and 16. Alright. Now suppose you want to grab all the values after this 9. So there are two ways you can do it. So one is what we learned earlier. So 9 is being pointed by number 4. So I'll just skip 4. So that means it has written 9. But I want to grab all the values after 9. So I can just simply put 4 colon and 14. The 14 will be last, or 15. Yeah. So it will be a last one. We have to increment by 1. So this is one way. Another way is that whenever you want to grab every single value after some value, you can just ignore the upper limit, or just don't put anything in upper limit, and it will behave exactly the same way. So after 4 indexing, every single value has been retrieved. Let's say I want to grab all the values are starting from 0 till 9. Same thing, I can do it. So first value, or I would say lower range, I won't keep anything. So just keep it blank and put 4. So from 0th indexing, 1 indexing, 2, 3, it has returned. Alright, so that is how indexing works in a one-dimensional array in a NumPy. Now two-dimensional array indexing we will see in a next video. Alright everyone. So let's continue our discussion on NumPy indexing and slicing. So in the last video, we have already learned about how indexing works for the 1D array. Now let's learn about the 2D array. So for that, first of all, we need one 2D array. So I'm just going to create the 2D array from this np range function only. So from, let's say 50 to 75, total 25 value we will generate it. So you can see here 1D array only. So I am going to apply one more function, which is a reshape. Although we haven't learned about this function yet, but subsequently we'll learn about all those manipulation you can apply on the top of this NumPy array. So reshape function accepts the argument like in which desired shape you want to convert your original NumPy array. So this is total 25 numbers we have generated, and in a one-dimensional format. So I just want to reshape it to the 5 rows and a 5 column matrix. And if I just execute it, you can see I have now 2D matrix or a 2D NumPy array. Alright. Now suppose I want to grab the individual rows, like first row, second row. It has total 5 elements. So same way, if I just do B0, you won't get just the 50, but you will get in this case the full row. So let me just execute it, and you can see, so first row we have extracted through this 0 indexing, because this itself is a one element. This is another element, or a second element, I would say. Same way, if you want to grab, let's say third, or it is being pointed to the 4th column. So it is 65 to 69. Now this is the row level indexing. Same way we have a column indexing also, because this is the 2D NumPy array. So same way the row has been accessed with the 0, 1, 2, 3 and 4 indexing. We have a column like 0, 1, 2, 3 and a 4. Now I will show you one standard indexing or a standard protocol to extract some data from this 2D array. Like first you can just simply give start to end for the row, and after comma you can just put start to end for the column. Alright. Now suppose I want to grab through this kind of notation the very first column. I can just simply use B. Now every single row I want to retrieve it. So as I told you earlier, whenever you want to retrieve every single value, just put the colon and leave it blank, comma, which particular column I want to retrieve. Let's say 0th column. So it has written 50, 55, 60. I'll just make it here row, and here column. Alright. Let's say the last column I want to retrieve. So I can just simply put 4 because last column has been pointed by the number 4. Suppose you want to grab the range of column or a range of rows. So you can see, let's say from 2 to 4 or 2 and 3. These 2 rows I want to retrieve it. I can just simply put 2 to 4 because at a row level you do not need to worry about which column you need to retrieve it. So you can see from 60 to 69 it has retrieved. Let's say you want to grab second row and this is the last row only. So the row starting with number 60 and 70 I want to retrieve. So in that case I have to give individual numbers like 2 and a 4. I just cannot put like a 2 to 4. So you can give all those numbers in a list. So this is called as a list and this outer bracket is called as a bracket notation. So don't get confused. So you can see 60 and 70 it has retrieved. Let's say you want to grab this 52 column and a 54th column. So that is being pointed by the number 2 and a 4. Same way. Now while retrieving the column, all rows I want to retrieve. So I'll just keep it colon and comma and then 2 to 4. So 52 or like. So I have just given here 2 to 4. That means 52 and 53 row. Let me just display B again so it will be visible. Now 52, this column and this one it has retrieved. Let's say I want to grab just the second column and a last column. So colon, comma, 2 and 4. So 52 and a 54th column it has retrieved. So this is the standard notation you can always use. Like first row level range you can give and after that column level range you can give. Whenever you want to retrieve every single value, you can just simply put colon either on a row level or a column level. And whenever you want to retrieve some specific column which is not a part of continuous range, you can just simply supply your all indexing value in a list. Alright, so now suppose instead of just full row and a full column, you want to grab some set of row with set of column. Let's say I want to grab this 57, 58, 62 and 63. So that is being pointed by this first column and then it's a first row and second row. Same way I have a third or a second column and a third column. So how will I write it? So first I have to go for row level stuff and both are separated by comma. 57 and 62 has been pointed by number 1 and 2. So I'll just keep 1, 2, 3 because upper limit is always excluded. Same way for the column 57 and 58, the number is pointing by 2 and a 3. So I'll just keep it 2 to 4. So you can see we got this 57, 58, 62 and 63. Let's say instead of 58 and 63, I want to grab 59 and 64. So in place of this 58 and 63, we want this 59 and 64. So row level indexing will remain same. So I'll just keep it 1 to 3. And at a column level, I have to keep it 2 and 4, not 2 to 4. So you can see I got this 59 and 64 in place of 58 and 63. So that is called as a slicing because you are slicing down your whole NumPy array. So we have gone through 1D indexing, 2D indexing and slicing. There is a one more like a Boolean indexing. So we have already created this A 1D array and we have a 2D array also. So let's apply this Boolean indexing on a 1D array. Let's keep it little simple. Let's say I want to grab all the elements which is greater than 10. I can just simply give A is equal to A greater than 10. So it won't return me all the element which is greater than 10, but it will return me wherever the values are greater than 10 will return a true, otherwise it will return a false. Now suppose the same masking, let me assign it to one variable like mask and I'll just supply it as a bracket notation, this mask. Alright, and now you can see it has returned me just 11, 12, all those number which is greater than 10. Suppose I want to grab all the values which is equal to 13 or which is equal to 5. Let's keep it simple. So let's say 5. So you can see first position only it has returned true, otherwise it has all returned a false. So wherever the values return false, it won't be retrieved. So what we can do, we can just simply supply this condition as a part of bracket notation in A. So you can see it has returned just the 5 only. Alright, so this way you can put all those kind of logical, mathematical condition, and based on those mathematical and logical condition you can retrieve the data. Alright, so that is all about the NumPy indexing and slicing. Alright, so array broadcasting. So what does the broadcasting mean? And to illustrate this concept, I have created the two sets of array. So let's just concentrate on a very first one. So it's a very simple one-dimensional array. Two array I have created, and both of them contain just the 3 number. So let me just execute it, and if I just display it, you can see both of them has a 3 values. Now suppose if I do very simple arithmetic like this, so it will do element by element operation like 1 plus 3, then 2 plus 4 and a 3 plus 5. So far so good and so simple. But suppose, let's say I want to perform the same arithmetic on a different shape. So for that, what I did, I just kept B as it is, A as a NP array or a NumPy variable. I have just converted into two-dimensional array. So if you just observe the A and B, you can see now A is a 4 rows and a 3 column matrix or a 2D array, and B is same as it is, like 3 values in it. Now suppose if I do A plus B, what do you expect as a result? So let's go to the broadcasting definition. So I have already opened this documentation for broadcasting in NumPy. So broadcasting says that whenever you want to do any kind of arithmetic operation, during that arithmetic operation, if the two arguments are involved which is of different shape, then how NumPy will handle, that is called as a broadcasting. So now if you observe here, we have a total 3 column and here also 3 values. So what happens that this whole 3, 4 and 5 will be added to the first row, then again 3, 4, 5 added to the second row, then again 3, 4, 5 added to the third row, and so on. So let me just execute it, and you can see 0 plus 3 become 3, 1 plus 4 become 5, and 2 plus 5 become 7. Same way whole array got added on every single row. So that is how NumPy do the arithmetic operation on a two different array which is of different in a shape, and that is called as a broadcasting. You can perform other operations like, let's say, A minus B. So it will be a 0 minus 3, then 1 minus 4 and 2 minus 5. Alright. So that is the basic concept behind the broadcasting, that how two different array of different shape can be added together and how arithmetic operation can be performed. Alright everyone. So how you can iterate over every single element in an array. So I have created here the two array. One is a 1D array and another one is a 2D array. So iterating over array, it means that you are trying to walk through of every single element in array. So let's say you want to perform some operation which is not inbuilt in a part of this NumPy. So in that case, you have to walk through every single element and apply those operations. That is called as a iterating over every single element in array. So let's try for the very first one. We are going to use the for loop to iterate over every single element. So for, let's say, element in np dot nd iter or n dimensional iteration, and we'll just supply a. So it will walk through every single element and put those temporary variable in this ELE variable. Let me just simply print it. So you can see, alright, I haven't executed this one. So let me just execute this one, and I have 2, 4, 5. We got this result from whatever the A we have created earlier. Let's go for the second one. So I can just simply copy this one and put it here. Let me just execute it. Now this is the 2-dimensional shape, and let's see how it will goes. So you can see it has iterated over every single element. Now suppose you want to perform some operation on the top of it. Let's say I want to add 3 to every single element. So now you can see 0 will become 3, 5 will become 8. Alright. So this way, now this operation is very simple and mostly you will get as a part of this NumPy library. But suppose some operations specifically you want to perform and iterate over every single element. In that case, you can use this ND iter. So that is all about how you can iterate over every single element in a NumPy array. Alright everyone. So now we have learned about how we can create a NumPy array through this NumPy library and some of the functions to create those NumPy variable. Now let's see how and what are the operations we can perform on the top of this NumPy array. And for that we need one NumPy array. So I'm just going to create a is equal to np arange function. I'm just going to use it. Let me keep it 30 and let me just reshape the same one, or reshape function I'll discuss. So earlier also we have used this reshape function. Now this a contains total 30 elements. Now suppose the same a variable I want to reshape it to 5 rows and a 6 column matrix. You can see it has been organized into 5 rows and a 6 column matrix. Let me just assign it to the B. Let's say same thing I can even organize into 10 rows and a 3 column matrix also, or you can even do 3 rows and a 10 column matrix also. Suppose if you just try to do some weird number, let's say 5 rows and 8 column, so it will immediately throws you the error that you just cannot reshape the array of size 30 into the shape of you have to reshape into 5 or you cannot reshape into 5 rows and a 8 column matrix. Alright, so now we have a B which is got reshape from the A. If you just apply B dot shape, it will return what are the dimension of individual axis of this B array. Let's say this 2-dimensional array, 5 rows and a 6 column 2D array, I want to flatten and I want to just put it into kind of 1D array. I can just simply use flatten function. So what flatten will do, it will just convert all your high dimensional data into a 1D array. There is a one more function through which you can even iterate over. So let's say we have already seen iterate in earlier videos. So b dot flat. So this b dot flat is a kind of iterable, and you can just simply print this temporary ELE. So you can see exactly the same data it has printed. Now let me just print this b again. Now there is a one more function which is equivalent to this flatten one. Let's say ravel. So you can use this ravel which exactly does the same thing. So it has also flattened this array from 2D array to the 1D array. Now in this case it has scanned this array on a row level fashion. So first row it has scanned, after that the second row and third row. Now suppose you want to scan this same array on a column level. So you can just simply use one more argument like b dot ravel and argument let's say c. So now you can see this is the default value. One more argument, it is being supported like when you want to travel through column level, so it will be a f. Now you can see 0, 6, 12, 18 and 24. So on a column level basis, it has done all those scanning. Let's say you want to transpose all those rows into column and column into rows. So there is a one built-in functions available, b.transpose. So now you can see all those row become column and all those column become row. There is a one more attribute true also. You can achieve the same task like b.T. Exactly the same result you will get. Now let me create a two array and some more operation like a concatenation, horizontal stacking, vertical stacking we will see. So I have a two array. Both of them are a two-dimensional array having a 4 values in a form of 2 rows and a 2 column format. If I just try to print this A and after that print B, you can see this is the first matrix or a first two-dimensional array and this is the second two-dimensional array. Now suppose I want to concatenate both of this array. I can just simply use np.concatenate and you can just simply supply all those series of NumPy array. So first array will be A and second will be 2. Alright, so there is a one typo and this is a type error. So it is expecting this all range of matrix whatever you can pass as a argument like a tuples. So first argument has to be tuples. And now the same result we got. Now you can see it has concatenated this two array into one single array. So it has done this vertical kind of stacking. So to do this concatenation, there is a two specific function is also available like np.vstack, and here also exactly a comma b you will pass it as a tuple values. So you can see exactly the same result we get. Let's say you can do even horizontal stacking also, AB. Now in this case you will get little different results. Now instead of stacking vertically, it will stack horizontally. So you can see 1, 2, 3, 4 as a first and a second column, and 5, 6, 7, 8 will be a part of third and a fourth column. Alright, so this is about concatenation. Let's learn about another one like a splitting. So here we have seen how you can combine these two matrix or how you can join two matrix or a 2D array. Now let's create one array and let's see the opposite function of this concatenation like a splitting of matrix. So let me create a very simple one. Let's say A range 10. Let's say I want to split this A, or let me just print this A once more. So it has a values like 0 to 9. So I'll use the split function on A and let's give the 5. So it has divided this whole array where having a total 10 values will be divided into 5 chunk. Let me create one more two-dimensional array. So I'm just going to use the same reshape function to generate the data. Let's say I'll just keep it 16 and reshape it to the 4 rows and a 4 column. Alright, let me display this B again. Now suppose all those splitting function I want to apply on a two-dimensional array. So we can use the one function like horizontal split. So here I can pass B and a 2. So it has divided this whole 4 cross 4 matrix into two different arrays. So first one will be 0, 1, 4, 5, 8, 9 and 12, 13. So first two column become our first matrix and a third and fourth column become our second matrix. Same way another function is like a vertical split. So you want to vertically split this matrix into two different chunks, or I would say first two rows will become first matrix or a first two-dimensional array and so on. Reshape function we have already seen earlier, so I am not going through again and again. Now some more manipulation like appending or deleting some element from the array, or I would say inserting some element, how we can do it. So let me just generate, we have already A. Let me create a having some more values. Let's say a range, just give 10 only. So same arrays I have created. Now suppose I have already 10 values in this A and I want to append one more values to this particular array. I can just simply use the append function, or append won't directly work on this A NumPy array. You have to use this np.append, and let's say 23 I want to add. Alright, so there is a one type error, so there is a one positional argument. So let's just see the documentation of this one. So first argument you have to supply like a for which array you want to append. So A comma 23. Now you can see the last element will be 23. Now if you again observe this A, still we haven't got this 23 as a last element to this A, because it has not done any kind of in place modification and it has generated a brand new completely different array. We have a two-dimensional matrix is also available. Let's say the same append operation we want to perform on this B variable, or let's say, so let's just start it. So B, and suppose I want to add 100, 101, 102 and 103. So I can just simply use 100, 101, 102 and 103. Now if you observe here, instead of passing just the one value, I have passed it the multiple values as a list. Oops. So we have a B variable. Let me just print B. So you can see it has flattened this array and appended this 100, 101, 102 and 103. Now suppose the same thing you want to apply at some axis level. One more argument you can pass it like axis 0. But in that case you have to pass it one more bracket. Now once you practice more and more, you will get to know about that why this axis or a one more bracket is required. So one more bracket indicates that you are trying to append completely different new row. Alright. Same way at a column level also you can append it. Alright. One more operation we'll see like a insert. So we have a 1D array like a 0 to 9 values. Let's say I want to insert, or I have to use like a np.insert. Insert. So here it will ask for the 3 arguments. Let's say I want to insert in a variable A, and the particular position where I want to insert, let's say the position will be 5, and what value you want to insert, let's say 100. So you can see now at the 5th position, or the position which is being referenced by the indexing number like a 5, it has inserted 100 and all the other elements got shifted to the right. One or more operation. Let's say you want to delete some value. So you can use the delete function. Let's say I want to delete 8. I can just simply use 8. And now you can see I don't have a 8 available in my return output array. Alright. So we have seen many functions which does all those kinds of array manipulation in this video. Some more functionality related to NumPy array we will see in our upcoming videos. Alright everyone. So now let's discuss about some of the binary operation which we can perform on the top of this NumPy array. So I have already loaded this NumPy library. Let's say I want to find the binary representation of some integer like np dot, we have one function available like a binary underscore representation, or in short it will be a REPR. Let's say I want to find the representation of 4, so it will be a 100. So that is like a very condensed representation of 4, only or a minimal amount of bit required only it will show. Let's say the same 4 I want to display it as a 40 bit. Let's say, so once you get the output you will get to know about that what does it mean. So you can see in a 40-bit format it has represented this number 4. You can do all those binary operation like a bitwise ending, bitwise ORing. So let's try a couple of them. Let's say np dot, let's say bitwise end. I want to do ending between let's say 5 and 0. So it will be, of course it will be a 0, because ending means whenever you have at least one value will be 0, the output will always be 0. Let's say between 5 and 5 you want to do, so it will be a 5. Or let's say you want to do between 15 and 15, so it will be a 15. Same way you can perform even bitwise ORing also. So OR operation circuit rule is that whenever you have at least one, regardless of other input, you will always get at least output in one. So np.bitwise ORing. We have other functions like bitwise NOT also and bitwise exclusive OR also. So let me just do 3 and 4. So we got the 7. So that is a bitwise ORing operation. Let's say 40, 3 and 40. So it will be a 43. We have a inversion of function also, like let's say invert. So let's say I want to do inversion of 10. So inversion of 10 will be minus 11. So it's a kind of 2's complement format. Let's say instead of 10 I want to do inversion of 0. So it will be a minus 1. If you want to get a very specific documentation of this inversion, you can just simply see here that what this inversion will do. It will just compute this bitwise NOT of this original representation. So there is a detailed documentation it has been given, and it shows that the inversion means the 2's complement of original number. You can even do left shifting and a right shifting also. So let's say I want to do left shift of 8 by 2. So it will be a 32. So it indicates that whenever you are left shifting, it is get multiplied by 2. So 8 got multiplied one time and it will become 16, and 16 got multiplied 2 times, it will become a 32. Let's say the same thing you want to do for 4 times, and you can observe the result that you got the result like 128. So it will be a like 8 multiplied by 2 multiply by 2 multiply by 2 multiply by 2. So you got 128. So 4 times you have to multiply by 2. Same way we have a right shift also. So it will divide this value by 2. Right shifting. So right shift. Let's say 30 you want to right shift by 2. And we got the 7. Alright. So these are some of the binary operation we have seen in this video. Some more mathematical operation we will see in an upcoming video. Alright everyone. So let's discuss about some of the mathematical functions available in this NumPy library. So NumPy has already built-in number of constants value also available. np dot let's say pi. So it will be a pi value, which is nothing but 3.14. Let's say you want to convert this radian value into a kind of degrees. So for that we have a one functions like degrees. You can even use the degree to radian also, and we have a degrees also. So degrees, let's give np dot pi. So pi value it will convert into degree, which will be nothing but 180. Let's say we are going to use this degree to radian. So 180 degree will convert into radian, which is nothing but 3.14, equivalent to pi value. We have a lot of other trigonometric function also built in inside this NumPy library. So let me create one NumPy array, and we will apply all those trigonometric function on the top of every single element available in this array. So let's say just 5 element I will keep it. And to calculate, let's say sine, we have a very simple sine function is available, and we will just supply simply a. So it will calculate the sine value of every single value available in this a array. Same way we have a cos also. So and we have a tan also. All right. You can even calculate the inverse of sine also. So there is a function like arc sine. So it will calculate the inverse of sine function. Same way we have a inverse of cosine, inverse of tan also available, Then we have a hyperbolic sine x, hyperbolic cosine, hyperbolic tangent function is also available. Let's see some more function like let's say you want to round off all the values. So round, I want to round, let's say 4.6. You can even supply whole range of values in a form of, let's say, NumPy array only. So it will be a 5.0. If you just keep it 4.2, it will be a 4. There is another two function like a ceiling. So let's say 2.4. So it will be a 3. We have a floor also available. Let's say 3.2. So it will be a 3. We have absolute value also you can calculate. So let's say you want to calculate the absolute value of -5. So it will be a 5. If you calculate absolute value of just the 5, it will be a 5. Alright. So this way you can just straight away use all those mathematical functions available in this NumPy library. So that's all about this video. See you into next video. We will see some arithmetic operation which we can perform on the top of this NumPy array. Alright everyone. So let's discuss about how you can perform the arithmetic operation on the top of this NumPy array. And for the illustration, I have already created a very simple one-dimensional 2 NumPy array, both of them having just a 3 value only. So let me just execute it. Now suppose I want to perform this element by element addition. So already earlier we have seen in this broadcasting video that how this concept of broadcasting will do all those mathematical and arithmetic operation you can very simply perform even if both of them or both the NumPy array of 2 different shapes. Here in this case the life is very simple. We have just put the 3 element and both of this array of the same shape. So if I just do a plus b, it will do the element by element addition. So 2 plus 5 will become 7, 3 plus 3, 6, 4 plus 2 will be 2. Same way you can perform a minus b also. So it will be a minus 3, 0, 2. You can even perform a multiply by 2. So element by element multiplication will happen here. And we have a division also. So it will return in a float value. Alright. So these are the same operation we can perform with the help of some special function available in this NumPy library also. So it will be a nt.add. So let's say you want to add 2 arrays, let's say a and b. So sequentially you can just simply append all those array. All those array will be added element by element. So exactly the same result we got. Same way we have a np.subtract also available. So it will be a comma b, and we have a np.multiply is also available. So it will be a comma b, and we have a divide also available. So it will do a divided by b. Alright, so exactly the same result we got. Apart from that, there are functions like reciprocal. So every single value will be divided by 1 and it will return. So so if you see here, 1 divided by 2 will return 0.5, but it has not written anything like a 0.5 because the original array was d type was integer 32-bit. So what we can do, either we can make this original array d type will be a float, or we can just simply supply one more array here. So let's say 2, 3 and 4, or let me just make one number as a float number. So it will return the reciprocal value of every single number. We can even calculate the power of every single number. So for that we can just simply use the POW function or a POWER, power. Let's say I want to grab the base of 10 and 20, and for both of them I want to do square. So 10 square will be 100 and 20 square will be 400. Now suppose For the first value, I want to find the power like 2, but for the second value, I want to find the third power. So it will be a 100 and a 8000 because 20 cross 20 cross 20 will be 8000. We have a modulo function is also available like np.mod. So it will find the remainder while you divide one number by the another number. So let's say 10, 20, let's skip it 30. If we just divide it by 7, what remainder we'll get? So if we divide 10 by 7, the remainder will be 3. 20 by 7, the remainder will be 6, and so on. Now instead of just a single number like 7, you want to divide every single number with a different numbers. So let's say first number I want to divide by 2, then 3, and let's say 5. So remainder will be 0, 2, and 0. Alright, so these are some of the arithmetic operation you can perform on this NumPy array. Alright, so that's all about this video. See you into next video. Alright everyone. So let's discuss about some of the inbuilt statistical functions are available in this NumPy library. And for the illustration purpose, I have already created one two-dimensional NumPy array where having a total 16 values are starting from 0 to 15. And it has been organized in a 4 rows and a 4 column format. Now suppose I want to grab the maximum value out of it. So we have a max function is available. You can just simply supply a, and across the whole array it will find the maximum value, which is nothing but 15. But suppose you want to grab the column wise maximum value, so you will get a 4 maximum value or a row wise maximum value. In that case also you will get a 4 value. How you can do it? So same function you can use it. Along with that, you can just simply pass on one more argument like axis is equal to 0. So it will calculate the maximum value across every single column. So on a first column, the value will be 12, then 13, 14, and 15. Same way, let's say if you want to grab the maximum value across the row, you can just simply provide this axis is equal to 1. So along the first row, the maximum value will be 3, then 7, 11, and 15. Same way, let's say you want to grab the minimum value. So I'm just going to copy this one, and we have an equivalent function is available in a NumPy library like a min. I'm just going to change it to min, and let me just comment the remaining two. So first will be 0 because the minimum value will be 0. Let's say across the column the minimum value will be 0, 1, 2, and 3, and same way across the row the minimum value will be 0, 4, 8, and 12. Alright, so these are the very basic and very simple functions are available. Let's go for some statistical function. Let's say we want to grab the range of like the difference between minimum value and a maximum value. So we can just simply use ptp function. So range will be 15 because the minimum value will be 0 and maximum value will be 15, and maximum value minus minimum value will be again 15. Here also you can just simply apply this axis equal to 0 and a 1, and respectively on a column level and a row level it will find the range. Let's calculate the mean value. Let me display a again. So the mean value will be a 7.5 across the whole array. Let's say the same I want to find across the column. I can just simply provide x is equal to 0. So it will be a 6, 7, 8, and 9. So it will be a middle value here between 4 and 8, between 5 and 9. And if you want to grab the same thing across the row, it will be a 1.5, 5.5, and so on. Same way we have a median also available. So median is nothing but the middle value 7.5. So if whenever you want to grab any operation on a row level or a column level, you can always use this axis argument. You can even calculate the percentile also. So percentile, let's say I want to grab the 50th percentile, or I would say that is nothing but a median value. Same way you can grab, let's say 25th percentile. So it will be a 3.75. You can even calculate the standard deviation variance also. So let's say np dot standard deviation, that how much your data has been spared across your middle value, or I would say mean value, average value. So it will be a 4.6. So this much data has been spared along the mean. You can even calculate the variance also. A variance is nothing but the square of this standard deviation only. So that will give somewhat similar result and similar kind of interpretation about the data. Alright, so we have seen some of the function like mean, median, percentile, how you can find a range, maximum and minimum. Alright, so that's all about this video. See you into next video. We will see some more functions about NumPy library. Alright everyone. So let's discuss about some of the functionality related to sorting and searching in this NumPy array. And I have already created one NumPy array of a one-dimensional where the values are like 2, 4, 8, minus 5, 5, 0 and minus 1. Let's say this data or this sets of value I want to sort it. So you can just simply use np.sort and it will be a sorted. So from lower value to the higher value it will be sorted. Now suppose if I just print a again, still you won't be able to see the sorted value. That means that all those sort functions are like a pure functions available in this NumPy library. It won't do any kind of manipulation or a modification on your original array. It won't do any kind of in-place modification, I would say. So it will return with a modified array, but that will be a brand new array, not modified in your original array. So if you want to put those into original array, you can just simply apply like a is equal to, so again a will be defined with a sorted value. Alright, but we don't want to do those things as of now, so let's just continue. So this is very simple. With just one simple sort function and highly optimized function has been written inside it. Suppose instead of sorting every single value, you want to find the location of sorted array. So we can use like arg sort. Now the first value after sorted will be minus 5. Now if you see minus 5 has been pointed by the indexing number will be 0, 1, 2 and 3. So the first value must be 3. Alright, so 3. Then the next higher value will be minus 1. So minus 1 will be a last value which is nothing but the index number by 6. So this way argument sort will give the index position of sorted array. You can even grab the argument or indexing of maximum value. So argmax function. So maximum value indexing position will be 2. Why? Because the maximum value will be 8 and 8 has been pointed by the number 2, indexing number 2. Same way you can grab like argument minimum also. So minimum argument will be minus 5 and it should be 3. Alright, so it is 3. Suppose you want to find the index position where the values are not 0. So for that we have a function like a non-zero. So if you just apply a, you will be able to see that there is no 5 here. Why? Because at a fifth location, or I would say this is the 0 has been indexed by the number 5 where it is pointing to 0. So it will return the index of all the values where the elements are not 0. We can even grab the function with the Boolean expression also. So for that we have a np.where. Suppose I want to grab all the values which are, let's say, greater than 2. I can just simply use a greater than 2 and let me display a again. So you can see it has written all those indexing position where the values are greater than 2. So this is greater than 2, this is greater than 2 and this one. So 1, 2 and 4 remaining all are less than 2. Suppose you want to grab all the values which is greater than 2. For that we can use the extract function. So first you can pass the condition and the second argument you can pass like on which particular array you want to apply this condition. So 4, 8 and 5. Now if you observe here 4, 8 and 5, all the values which are greater than 2. So extract function will return the actual value, whereas the where will return the index position of satisfied condition. Alright, so that's all about how you can do sorting in this on the top of this NumPy array, and based on some condition how you can search some particular element in the NumPy array. Alright, see you into next video. Alright everyone. So two very important concepts like a copy and a views, and both of them are functions in this NumPy library, and this thing we are going to see in this video. But before that I want to introduce one more concept like a identifier, and those identifier is not a part of NumPy library but it is a part of core Python only. So let's say I'll create one NumPy library or a NumPy array I would say, and let me give very simple 2, 3 and 4. Now suppose on a memory, not on a physical memory but on a Python virtual machine, I want to find the identifier or some kind of memory location or some kind of address of this particular variable. There is a inbuilt function available in this core Python like a ID. Although we haven't discussed this function earlier because this is not a part of NumPy library but it is a part of core Python. So suppose if I execute it, it will return me some number. So that looks like a garbage for us, but based on this number only, this Python virtual machine, Python interpreter will do all those jobs for us. Now we do not need to bother much about this particular number, but the concept which I want to introduce is that now A is been pointing by this particular number. This is called as a kind of identifier or some kind of unique identity on all those variables, functions are available in this Python virtual machine. Now suppose I'll create one more variable, let's say B, and I'll just point it to A. Now if I try to do id is equal id function and I'll just apply B, I have got exactly the same number because I have equated this B is equal to A. That means that this both the variable A and B has been pointing to same memory location or a same identifier where our actual data 2, 3 and 4 reside. Now suppose we'll make some twist here. I'm just going to change the very first value of this A array, or I would say A, and let me just make it -5 and let me just execute it. Now suppose if I try to print A and B again, what do you think that effect will come? The first value in this A NumPy array will be definitely changed, but what about B? Because B is also pointing to same one. So you can see the effect comes on both the place. That means that whenever you are trying to equate the reference this way, they are not going to create any kind of physical copy on a different location on your hard drive. Python virtual machine will not do it. Instead of that, whenever you try to change on a one reference only, it will be affected to another reference obviously whenever you equate with this way, because A and B both are pointing to a same memory location. So we try to change those particular memory locations value only. Alright, so suppose we want to avoid this situation and we want to create a perfectly different physical array, or we want to make a copy of physical array so that whenever you change on a one array, it won't be affected to another array. So we have to go for the concept like first view and then for the copy. Now let me just copy it again. So for your reference, it will be very much helpful. So another concept we are going to learn now, view. Now if I just do id A, you can see I just got the different memory location because I have executed this A variable again. Now I will create B is equal to not A but A dot view, And if I try to find the identifier of this B, you can see now we have two different memory location for two different NumPy array, A and a B. Suppose the same operation if I perform again, definitely the first value in this A NumPy array will be changed. But what about B? Let me just print both of them. So now again the same situation arrives even if we have used this B or a view function. The effect comes on both of this array. Why? Because view will just create another reference location only. So B is pointing to another location, but that is eventually going to point to the same physical location. So view is kind of working this way only, but view will create another identifier at another memory location. But actual data will not be copied to another memory location. That's why whenever we try to change the value in a one array, it has been affected to another array also. Now another concept we'll see like a copy and how copy function will resolve this thing. So same array we'll use, and let me find the identifier for this A. So again I got a different identifier, but now for equating I am just going to use A dot copy. Now this function again create a different identifier for the B. So identifier for the A and B will be different, but now in this case the copy will actually copy all those data into some other memory location and create a reference name as a B. So suppose if I try to do A0 and equate it to -5. Now what do you think what will happen? That A array will be definitely changed, but B will not be changed because this copy function has actually copied the same data 2, 3, 4 on another location also. So we have just now changed on a one location only, which is nothing but the reference by A, not by reference B. Now if you try to do, let's say B1, let's say 400, and if you just print A and B again, you can see it has affected the B NumPy array, but it has not affected the NumPy array A. So copy function will be very useful whenever you don't want your original array or some other array, you want to take it as a backup. You don't want it to get affected. So what we did throughout this whole video, let's just recap it. So in the first case, we have just equated this way, but in this case, the reference is also same and it has been affected to both of this variable or both of this array. Second time, we use this function like a view. So in that case, it has created a two different identifier with a two different numbers, or I would say location, but it has not still affected or actually it has affected both of this variable whenever I try to change, because this view function will not create the actual physical copy of the same array, but at the end we use the copy function, and this copy function has created copy of actual data on some other location in your memory. That's why whenever you try to change one, it has not affected the other one. Alright, so that is all about what copy and views in this NumPy array. Alright everyone, so let's discuss about some of the inbuilt functions related to linear algebra which is available in this NumPy library. And I have already created one two-dimensional matrix for the illustration purpose, which is having a 3 rows and a 3 column. So let me just execute it. Now all those functions available in this NumPy library, which is a part of this lineage module. So every single function we are going to access inside this lineage only. Now suppose I want to grab the rank of this matrix. I can just simply use matrix rank and just supply A as our input argument. So this is of matrix rank 3. We can even grab the trash of this function. So trash will be nothing but addition of or a summation of all those diagonal elements, which will be a 2 plus 9 plus 8. Let's say you want to grab the determinant. Now this trash is a part of NumPy library core module only, whereas to find this determinant we have to go inside this lineage module. So np.lineage.det determinant. So it will calculate the determinant 186. If you don't know about determinant, you can just simply search on Google and go to the Wikipedia link. It has a very nice mathematical equation that how the determinant of any square matrix will be calculated. You can even grab the inverse function easily, like np.lineage.inv. So this is the inverse function of our original array. Let's say you want to grab the power of matrix. So third power of this matrix I want to grab it. So this is the third power. We can even grab the eigen value also. Now we are not going to go into detail of how those linear algebra theory works, because my idea in this course is to explain you that how you can use all those inbuilt functions available in this NumPy library. So np lineage.eig eigen, you can just simply apply a. So it will return with a 3 eigenvalues and a 3 eigenvectors for our original 3x3 matrix. We can even grab the singular value decomposition of our matrix also. So for that we can just simply use svd function and it will calculate this svd. So svd is nothing but like a decomposition of your original matrix. So it has decomposed our original matrix into 3 different matrices. So this is the first matrix, this is the second matrix, and this one is the last third matrix. Let's say you can even solve some linear equation also. So let's just create one very simple linear equations like let's say x plus y is equal to, let's say 5. That will be a first equation, and the second will be, let's say 2x minus 5 will be a 10. We want to put this equation in some form of NumPy array, and we will tell this linear algebra module to solve it. So let me create one variable. So first matrix will create having all those coefficient on our left hand side like a 1 and 1 and 2 and minus 1, and another matrix having a values like 5 and 10. So a NumPy array. Now here we are going to use this 2D matrix. So first will be a 1 comma 1 and second will be 2 minus 5. So these are just the coefficient of our original equation which we want to solve for x and a y. And another array we will create like np.array. We will just supply the coefficient or a constant value on the right hand side 5 and 10. Alright, so now we have a and b got defined. Suppose if we want to find a solution for this, we can just simply apply np.lineage.solve. So it has written 5 and 0. That means the value of x will be 5, which satisfied both the equation, and value of y will be 0. Oops, it will be a 5y. Alright, so these are the very few functions we have seen about the linear algebra. You can just go through the documentation of this linear algebra. There are many more functions. You can just walk through it. My intention is to just give you an idea that how you can just use those ready-made inbuilt functions available very fast. Alright, see you into next video. Alright everyone, so we have created a NumPy array. We have done all those kinds of mathematical operation, logical operation, all those kinds of manipulation we have seen throughout this whole course. But suppose you want to persist all your data into some kind of text file or some kind of binary file. So how you can do it? And once you persist all those NumPy array, because that is nothing but a basic core fundamental data structure or a data type available in this NumPy library. So it is a very good idea to persist all your modified version of your original array when you are dealing with a very large scale data processing. So in this video we'll see how you can store your array into some kind of file. So let me create one very simple 1D array. Let's give the value like 2, 5 and 7. Let's say I want to save it into one file like np.save function. I can use it. So first I can give the argument like binary file. In a binary file I want to store it. So out dot, let's say, bin, and which particular numpy array I want to store it. So A. Now if you go to the Explorer, you will be able to see there is a one file called as a out.bin, and automatically this .npy extension got appended. If you just open it, you won't be able to see anything because this is completely serialized and binary data. So let me just close it. Now suppose the same data you want to again read it. You can just simply use the load function, and here you can just simply supply out.bin.npy. So you can see exactly the same data we got, 2, 5 and 7. So this time we have saved this data into some kind of binary file, but suppose you want to save it into some kind of text file. So you can use like a save text function. Let's say data.txt, I will give the name, and which particular variable I want to save it. So A. Now if you go to the Explorer, again the new file got created like data.txt, but now this is the human readable file, so you'll be able to see what data it has stored in this data.txt file. Alright, same data if you want to read it, you can use the load text function and just simply apply data.txt. Oops. So it has written 2, 5 and 7. Alright, so this way whenever you want to persist your numpy array on some kind of binary file or some kind of text file, you can do it. And with the help of this load text or a load function, you can read and put all your data from persisted file into kind of numpy array. Alright, so that's all about this video. Alright everyone, numpy exercise problem. So to check our understanding regarding to various concepts we have learned in this numpy library, I have created here the 4 problems, and all those 4 problems are quite descriptive. So before I start working on the video solution of every single problem, I would highly suggest you pause this video and create your own solution and check with mine. There are number of possible solutions for one single problem is possible. So it's always up to you that how intelligently you can use the different functions we have learned in this numpy library. Alright, so just pause video and start working on your own solution, and I'm just going to continue with the solution now. So let's see the first one. We have been given this below array. So let me just select it. Before that, let me run this import statement from this numpy, and array got defined. Now in this we have to write one expression which will replace all the negative value in this array with 1000. So in place of this -3 I have to replace with a 1000. In place of this -5 and -1 also needs to replace with a 1000. So one way we can go with like you can just find the indexing position of this array like 2. So 2 is pointing to -3 and just equate it to 1000. And you have to write a 3 expression and it will work. But we don't want to go with this way. We will go little intelligent way. Let's say I'm just going to do the comparison with 0. So it will return me like a Boolean condition I am going to use. So it will return me all the places where the values are negative, return true. So you can see I got true wherever the values are less than 0. Now suppose if I supply array and condition in a bracket, so you can see all those negative value, I got it. Now suppose if I equate it to 1000, so all the values which are less than 0, the index will be given by this particular expression will be equated to 1000. And suppose if I display array again, you can see in place of -3 now got replaced with 1000. In place of -5 and -1 also got replaced with 1000. So that is how you can use it. This binary condition to replace all those negative value with 1000. Let's proceed for the next one. So here we have given the array where all the values are 0 and 1 only. Let me just select this one and let me create an array. Let's say A, and I'm just going to use this array function. Oops, this array is not a part of. Alright, so array got defined. It is a two-dimensional array, and we have to find how many ones inside this array. So we can use the Python inbuilt function also, like we will just sum over every single column first. So you can see in a first it will be a 5 ones, then 8, then again 5. Suppose if I apply the sum over sum again and again, it will return me 62. That means total 63 places there is a 1, and eventually we have calculated that there are total 62 ones are there in this 2D array. But we have used this Python inbuilt function. Suppose I want to use this NumPy function. We can just simply use np.sum and I can just give array. So it will also return me 62. You can even calculate the column wise sum also, like np.sum, but it will be a little complicated way. So it is not advisable to go that way, because with just the simple expression we got our result. Suppose if I do array and I'll just supply x is equal to, let's say 1, it will be arr. Alright, and again if I do sp.sum, so it will be 62. So this expression also returns the same thing. Suppose instead of x is 1, I'll just do x is 0. So again I got the 62. So there are a number of ways possible to get the same answer. Alright, let's proceed for the next one. Let's say we have to create a one NumPy array where all the values are between 1000 and 2000, and all numbers should be divisible by 5 but not with the 15. So one thing what we can do, we can iterate over every single values between this 1000 and 2000, and we can check whether those number is divisible by 5 and not divisible by 15. If those condition got satisfied, we will just include it. So let me just hop over to, let me give the temporary variable like I, and I'm just going to use the function like range. Alright, so between 1000 to 2000, and let me just print, let's say I. So it will return me all the values. Now we need to calculate only those values which are divisible by 5. So what I can do, I can go in a step of 5. So you can see some more values got reduced. So from 1000 to 1005. But here we got all those values which are divisible by 15 also. So how we can remove those things? So one more condition we can add it here, like if let's say I modulo 15 is not equal to 0. That indicates that if the number is not divisible by 15, then only include it. So you can see some more number got reduced. So 1005 got reduced. Let's just calculate whether 1005 is evenly divisible by 15 or not. Alright, so it's a 67. That means it got removed. So this way you can go ahead. So here we have used the inbuilt function available in this core Python. Let's proceed with some of the functions we will use from the NumPy. So we can use the np.arange function, and from 1000 to 2000 all the values it will generate. Let's say in a step of 5 I want to go. Same way we have used this range function. Again from this particular array I want to remove all those values which are not divisible by 15. So what we can do, array modulo 15, again the same condition I can apply, is not equal to 0. That means it will return me true whenever the 15 is not divisible by 15. So I can just simply use this condition as a part of bracket notation in this array variable. So now you can see exactly the same array I think we have got. Yes, 90, 90, 90, 85, 90, 75. Yes. So 3 problem got finished. Let's proceed for the next and the last one. So here we have to write the function which calculate the standard deviation of one-dimensional array. So one sample one-dimensional array I have kept it here. So it will generate the randomly or normally distributed data where the standard deviation is by default 10. So it will generate all those data where the standard deviation is 10. Now there are two ways we have to compare this standard deviation. One is we have to write our own function, and this particular function with the help of different NumPy function we have to calculate, and those results what we got from our function we have to compare with the inbuilt function available in this NumPy library. Alright, so first let just use the standard function like np.std, and if I just apply a, so it has returned me the standard deviation like 9.04. Now with our function also it should return exactly the same result. So I'm just going to create a new function like def, let's say cal underscore std, which accept this arr array variable. Now first things we have to calculate the mean. So I am just going to use min, say np.min a. Alright, so min got calculated. Next is we have to subtract every value of array from this mean value. So I am just going to define new variable like diff. It will be a minus min. So every single value in a got subtracted by mean value. Alright, now I have to take the difference square. So I can use the sqre square np dot, we are going to use this power function. So power, so every single value's power I have to calculate like diff, and which power I have to calculate? 2 divided by what is the size of array. So we can calculate this size with a number of different ways. So we are just going to use inbuilt Python like length of a. Alright, so we got the square and divided by n, or I would say the length of this array. Next is square root. So I'm just going to give the new variable like root. Now I have given this 4 different variable I have created just to explain you and you can understand it easily. Otherwise we can even wrap it all those 4 variable in a one single function is also possible. So whatever we got square, now we have to take a square root of it. So I can do one thing like np.power, the same function we will use power, but now instead of square I have to take a square root. So for that the exponent I will write like a 0.5. Alright, and at the end I am just going to return the root variable. Alright, so our function got defined. Let's see if any errors will get or not. So cal standard deviation, calculate standard deviation. Let's say I'll give the a as input. Oops, so something we made wrong. Alright, so there is a one mistake we have done, like we haven't calculated the sum. So you can see we have to the difference, sum of all differences. So here we got the differences. Now after that I am just going to apply, either you can apply this difference, no, after square I have to take a difference, so I have to apply it here only. So I'm just going to use np.sum, because I was expecting just one value and it has returned me lot of values in output. Alright, so I have re-executed this cal underscore std function and you can see. Alright, so we have exactly got the same result. There is no even a single decimal got changed, 0.4594. So exactly the same implementation we may found in a NumPy original source code, but they have implemented in a C language way. Here we have used the inbuilt NumPy library function. Alright, so this is all about the exercise problem in this NumPy library. Alright everyone, so let's solve one exercise problem to check how much we have understood whatever we have learned till now. So here there is a 2 arrays has been given. So we have a one array like a where it is a one-dimensional array, and we have to produce the array B from the array A. Like any kind of arithmetic you can apply on the top of original array A, and you need to produce the array B. Alright, so let's try to observe that how we can do from here to here. So first observation says that it has a number of zeros and ones only. So one thing we can do it, we can first create a array where all the elements will be 0, and how we can create and initialize the element with zeros we already know. We can just simply use the zeros function. Alright, now if you observe one more thing, that on every single row or on every single element available in this B, there is only one place there is a 1 value, otherwise all are 0 only. One more thing, that there is a, how many elements are there? 3, 4, 5, 6, 7, and there is a 10 elements are there. Same way in B also there is a 10 elements are there. 1, 2, 3, 4, 5. Yes, there is a 10 element are there. Now one more key observation is that now if you observe a very first record or a first element in this B, at a 4th position only it is a 1. Then we have a 5. So at a 5 position only it is a 1. Then 0. So at a 0th position only it is a 1. So what we can do, we can iterate over every single element available in this A, and based on those value we can find the indexing position in B and just skip or update those particular element with 1. Before that, as we discuss, let me just write solution heading. Alright, so let's first create another array, like let's say ARR, and I'm just going to use this zeros. Now this zeros has a total 10 rows and a 6 column. If you observe here, always there is a 6 column. So we already created the array where all the values are 0. Now next task for us is to just put 1 at a place where the indexing value has been given by the NumPy array A. So let's just enumerate this one. Now here we'll keep like a temporary variable in, and we are going to use this enumerate. Now why this enumerate in this A NumPy array? Because along with the iterating over every single element, we need indexing 0, 1, 2 kind of looping number also. So there is a 2 variable it will always return, like I and element. Let me just print both of them first of all, so you will get the idea that for loop has to be like colon I and ELE. So if you see here, the I will be 0, 1, 2 up to 9, and ELE will be all those values available in this A array. Now what we need to do, let me just comment this one. We are going to update this our ARR array with value 1 time only. So for every single element available in A, like 4, so second indexing value we will keep it like ELE, and first will be I. So what it will do, it will try to update 1 at a position I comma ELE. So first time it will go through, it will take 4, so the value of ELE will be 4 and I will be 0. So 0 comma 4 position it will update 1. Next time we have a 5, so 1 comma 5, because we have to update at a second element only. So I will be helpful for iterating over every single element, and it will give the values like 0, 1, 2 up to 9, because we have to update all those 9 elements. While updating this ARR variable or array variable, we have to keep the track of this row number also. Alright, let me just execute it and let's just display ARR. So exactly the same value we got it or not. So let me execute this B also, and now what we'll do to check our all values will be correct or not. So we can just simply subtract this ARR minus B. So you can see every single values will be 0. You can even apply the sum. So sum has to be 0. So this indicates that exactly the same array we have reproduced from this our original array from A to B. Alright, now why this kind of thing I have put it into exercise? Because this is the very real life problem. So once you learn about the machine learning stuff, specifically the supervised learning or a classification related problem, most of the time we have to convert this kind of thing into this kind of array. Why? Because whenever you have a discrete amount of category available in your output, you have to put it like at a 4th position only it will pop up. In second time at a 5th position only it will pop up. So this way this classification problem will work. So those of you who already know, that is called as a one-hot encoding kind of technique. So from here to where we have reached, that is called as a one-hot encoding. And this is one of the very important technique while solving any kind of classification problem in a machine learning world. Alright, so if you want to know more about one-hot encoding and its interpretation, just search on a Google and go to any Wikipedia or best resource available on internet. So you'll get the idea that why this real life problem I have included here. Alright, so that's all about this video. See you into next video. Hello everyone and welcome back. So image is into a kind of NumPy array. So in this video we will see how we can convert the image data into kind of NumPy array. Now this is the very first practical application we are going to see of this NumPy library. But why we need to convert all your image data into a NumPy array kind of data type? When you go for very high level modeling stuff like applying any machine learning algorithm or a deep learning algorithm, you need all those data into kind of number format. And for that I have already kept one image. So let me go to the Explorer and you can see in a notebook folder I have kept here the numpy.png file. So this file resides on a same directory where I have created this Jupyter notebook. Now this image we are going to read in this video and after that convert it into a NumPy array. Now after reading directly it will create the NumPy array and all those operations we have learned which we can apply on NumPy array we can apply on this image afterwards. As I told you, whenever we go for very high level modeling of any kind of data, let's say from this image we want to find what are the characters are involved in this image like N, U, M. So that is the problem of character recognition. So the first foremost task in any machine learning kind of application, you need to read your data, put it into some proper format. And in a very first video I have already introduced that why NumPy, because for majority of data science package this NumPy is a basic building block. Alright, so let's go to the Jupyter notebook and we are going to read this numpy.png file. So let me import one more library like matplotlib. Now inside this matplotlib library there is a one function is available inside this image module of this matplotlib. So I am just going to read this imread function. So inside the matplotlib.image there is a one function available imread. So imread. Now here as argument we can supply this numpy.png file. Alright, and let me just assign it to, let's say, nmpy. I could have write this numpy, but that is a reserved keyword. You can always use it, but still it will mash up with the all reserved keyword available in this NumPy library and Python. Alright, so we have successfully read this file and put all our data into nmpy variable. Let's try to find the type of this nmpy. So it will be a numpy.nd array. So all those numbers and data are available in this image file. Let's go to the image file, like every single pixel value which is been characterized by the 4 different numbers in case of this PNG file, like one channel is a red, then green, blue, and one is for the transparency. So all those data has been read and put it into NumPy array. Let's try to find the size. Let's say NumPy array dot size. So it will be a little bigger number. So you can see it's kind of 2.2 million, you would say. So this many amount of byte are required to store this image. Let's try to find the dimension. So numpy dot ending. So it will be a 3. So whatever output we got, that is a 3-dimensional array. We can even grab the shape of this numpy. So that will be a 3-dimensional array. First axis is 475, second axis is 1200, and the last one is a 4. Now what does this 475, 1200 and 4 mean? So 475 is nothing but the total rows. 1200 means how much wide your image is, that is a 1200. And a 4 is nothing but the total number of channels used in this image, like red, green, blue, and 1 is for the transparency. Alright, let's grab some data. Let's say I want to grab just the first channel. So all row, all column, or I would say every single data of first axis, every single data of second axis. But for the last axis, I am just going to put 0. So first channel value, it will return. So you can see mostly you will be able to see majority of 0 just because there are many values are 0 here. But when you explore this thing, you will be actually knowing that there are data exists. So for this particular, let's say pixel, if you want to find what are the pixel value, let's say we'll go somewhere here. So whole height is 475. So somewhere around 200 and somewhere around 200 on a width level also, we'll try to find what are the pixel values. So we'll get some numbers. So you will get idea that everything is not a 0. So 200 cross 200 and every single value in a fourth axis. So you can see we got this 4 number. So that means 1 is for red, green, blue, and 1 is for the transparency. So if you observe here, somewhere around here we have got this pixel value. We extract this pixel value the way we have seen in this indexing and a slicing video. Alright, so that is how you can convert your image data into NumPy array.